Okay, so we were in the Fourier transform. Finally, the graph Fourier transform. So Fourier transform, what Fourier transform does, takes a thing and express it in terms of other things. Oh, well, that's a simplification. That's an oversimplification, I would say. But this is what's happening here. We have a function f on a graph that's a function from all vertices to a real valued vector. And in this case, our function f will be a value of a time series at a particular time. Our f simply is the value of that time series. So a function f looks like this. Takes v vertices 1 2 3 4 up to v and goes to v dimensional real valued function. Okay, so that's our function. That's what our function is. So we have this function and we want to represent it in terms of other. Now it's just represented in the traditional way we know it is represented, but we want to represent it in terms of our basis vectors that we have chosen. So we have gone to so much trouble to obtain these particular eigenvectors. So here UL is those bases or eigenvectors, and lambdas are the eigenvalues. So what this signifies in if we take an analogy to a time series Fourier transform, the UL is that e to the power iota pi something something, and lambdas are those frequencies basically. So this is what we are trying to do. We are trying to somehow convert our graph from a discrete data structure to a graph spectral data structure. So for all I equal to 1 to n, we have our function I and we have multiplied with a particular basis vector and we are adding that, right? And this is what we are doing for one eigenvector, and when we do it for all eigenvectors, this is just a u of L. When we do it for all possible L's, we'll have the entire Fourier transform of the graph of the. So I hope I've given you a moment to think about it. But as you can see, the inverse graph Fourier transform is also not that different, because what we do is take those eigenvectors, multiply them with their particular coefficients and add them all together. And our hypothesis is that all of them will come together to form the original function f of I. That's what GFT is. That's what Fourier transform is. So what Fourier transform does is the eigenvalues of L, the Laplacian, play the role of frequencies and the eigenvectors, the Fourier basis. The graph Fourier transform and its inverse gives a way to represent a signal in two different domains, the vertex domain and the graph spectral domain. So the vertex domain is something the red lines over here represent, and the graph spectral domain is the blue plot here, and also the blue lines which are given on each particular node. That's what the spectral domain is. So why did we bother doing all this? So after graph Fourier transform, you are here. Now, what graph Fourier transforms give us is a representation of how this graph is behaving, of what frequencies or what is the spectral properties of this graph. So what we can do is leverage this information, and we stand a very good chance to learn the inter-series dependencies and how in itself this graph is functioning. So what the statement here means, now we stand a very good chance to leverage this graph structure and learn some crucial inter-series information thanks to the spectral domain of graphs. So instead of just looking at graph as a data structure, what we are going to do is look at the graphs in this spectral domain and learn intergraph series, intergraph dependencies in this spectral domain. So we have a very good base now that we can learn inter-series dependencies. But first, let's learn some intra-series information. So earlier also I mentioned that this how Microsoft stock behaves in of itself and how it behaves with Tesla, Google, Amazon, and so forth. So after GFT, we have n time series in graph spectral domain. Okay, n time series in graph spectral domain. What if we do a discrete Fourier transform on this time series? We have n time series in graph spectral domain going to frequency domain in graph spectral domain. So we are going two levels deep right now. We are two levels deep. In first of all, we are in the spectral domain of the graph as, and now we are in the spectral or frequency domain of the time series. So now we do 1D convolutions and apply GLU activation and inverse DFT. Okay, what does this mean? So first of all, discrete Fourier transform. Again, I'll sound like a broken record, but this is what Fourier transform is: express one thing in terms of other things. Xn here is one thing, and e to the e raised to iota 2 pi over n kn is other things. So e raised to minus iota 2 pi over n k, and that is our basis vector. So this is basically nothing but a basis change. That's what Fourier transform is. In mathematics, the discrete Fourier transform converts a finite sequence of equally spaced samples of a function into a same length sequence of equally spaced samples of a discrete time Fourier transform. Just skip over the fact, and it's just that we are doing from n time points, we are going to n frequency points, and that's what discrete Fourier transform does, and its inverse is also the same. So now what we are going to do is do 1D convolution on whatever the outputs, whatever the n outputs of this discrete Fourier transform is. Why did we bother going to the Fourier, going to the frequency analysis? Because the hypothesis is that doing 1D convolutions and trying to learn stuff in the frequency domain of a time series is going to be more beneficial rather than just looking at the time domain. So that's what the paper is trying to do. So specifically, the output of DFT has a real part and an imaginary part, which are processed by the same operators with different parameters in parallel. So let's first of all look at what this GLU is. So I'll bring you to the bottom of this slide. GLU of two vectors A, B is A and a Hadamard product with sigmoid of B. So this is a pointwise multiplication, so to speak, of A and sigmoid of B. So here what B tells us how much of that particular row in A is allowed to flow forward. And as you know, sigmoid is a function like this. So the if B value is high, then the number is almost 1. And when the B value is low, minus 1000, minus infinity, the number is almost 0. So wherever B's value is high, that particular row of A is allowed to flow forward, and where B is low, that particular row of A is stopped. Information flow in of that row is stopped. So that's what is happening is here. That is what is happening in this equation number 5 from the paper. The GLU is acting on A and B. In this case, A and B are same. This is just an architectural choice. So theta here is the 1D convolution with kernel size 3, and 1D convolution on that DTFT in graph spectral domain. And we are going to do a Hadamard product with a sigmoid of itself. This is just how the paper is structuring it. And star can be real or imaginary. So this is basically this is the same equation, same for imaginary, same for real parts, and these both can go in parallel. And when we have the output of the GLU, we can reconstruct original signal by doing an A plus iota B sort of calculation over here and add the real part to the imaginary part. And we can go the inverse DFT, and then we have obtained some intra-series info. We have obtained the hypothesis is that we have learned some things from within this series, and the learning part occurs in this theta star convolution. Other than this, all is simple mathematics, but theta star convolution is it looks at a particular frequency and it looks at the particular frequency on the right and to the left and does a convolution and tells us how much, what is the representation of this particular time series. So after this DFT, 1D convolution, graded current unit, and inverse DFT, you are here. This is just before graph convolution. So graph convolution. This is a technical concept. This is a good concept, so to speak, and I had fun when learning this. So first of all, let's think about what normal convolution is in the CNN sense. So in a CNN, we have an image. For example, this image of what I think is the tail lamp of a car, and it has pixels. It has a 2D very highly ordered pixels, and what we do is we layer on top of it a kernel with J1, J2, J3, J4, J5, J6, J7, J7, J8, J9. This is a kernel. And what we do is do a pointwise multiplication of each of these with the image in there, and we add them all up together, and then we tell that this is a convolution of this kernel for this particular pixel. For example, let's look at this right hand side image. We have our image which is denoted by the black grid, and our convolution kernel which layers on top of that image, and it fits in very nicely, and then calculates the products, and then we add them up together, and the processing is carried forward. But this kind of convolution cannot be directly applied to graphs. Well, why? First, in a graph, there is no ordering of the nodes. For example, there is no notion that J2 comes after J1, J3 comes after J2, and for an image, pixel 1 is before pixel 2, is before pixel 3, is before, and so forth. In a graph, there is no such thing, because a graph uh, it's just a data structure. It's just organized in such a way. There is no notion of the top right corner of the graph. For example, this is a graph representing you in Facebook and me on Facebook. And if we were to do a convolution on you, what will be top right of you? What will be bottom left of you? And how will a convolution kernel layer on top of you? And how will it calculate? How will it multiply and add them all? Add these things together. There is no notion of top right corner of the graph. There is no notion of up, down, left, and right. In this case, it was a well-defined notion, because we have an image which is very highly ordered, which is a very highly ordered graph. There is an up, there is a down, there is a right, there is a left, there is a northeast, there is a southwest, and so on. But for an arbitrary graph, that's not possible. The second issue is, so like before going to the second issue, let's focus on this. Node J has no specific position. It's just an arbitrary index. And how would you go about layering a convolutional filter in this on a graph? The second issue is neighborhood sizes may be different. For example, in our very beautiful and ordered example, J5 node has 1, 2, 3, 4, 5, 6, 7, 8 neighbors. And this is always going to be the case wherever you go in the image. Each and every node in the image will have 8 neighbors. But that's not true in a graph, in an arbitrary graph. So the weights shown here as 4 nodes, but node I in the right hand side graph has 7 nodes. So how can we do a convolution on these? How can we ever do a convolution with such a case when the number of nodes itself is different between the kernel and the graph, right? So I hope this is understood, like, because there is no notion of ordering, and there is no notion of neighbors and how many neighbors, you cannot directly go about doing a convolution in the convolution sense, in the CNN sense on the graph. So there needs to be something different when we are doing graph convolution. So, okay, this is a slide. This is going to take a little bit of your involvement. We are going to redo things a bit. This is just in order to have, a standardized, normalized way of representing things, so that whenever you are also studying it in the future, you don't get confused by my representation. So, graph G is vertices, edges, and adjacency matrix, right? And this delta n cross n is the Laplacian, where Laplacian earlier I denoted by degree matrix minus adjacency matrix. We are trying to normalize this in such a way that the Laplacian is identity minus uh, degree matrix raised to minus half times adjacency matrix times degree matrix raised to minus half. This can be very easily be done when we are doing when we do some factorization of that matrix, and we're just trying to normalize it such that uh, there is some property with this particular Laplacian where capital D is the diagonal elements with sum of all AIGs. That's the same thing. That's all the same. So the following is the eigen decomposition of the graph Laplacian. Because it is a symmetric and well, it's a symmetric real matrix. We can decompose it in, as Gilbert Strang would say, any symmetric matrix is Q transpose lambda Q. Let me rewrite it. Q transpose lambda Q, and all of these Q's are orthogonal, and this is the diagonal diagonal matrix with eigenvalues. So that's what it is. Laplacian is a symmetric matrix, and we are going to factorize it in phi transpose lambda phi. So Laplacian is factorized into three matrices. Okay. Phi is defined below. It contains column vectors or lab eigenvectors phi 1 to phi n, each of size n cross 1. This is basically the eigenvectors of L, but they are normalized in, and those are also the Fourier functions because we have decided that they are the Fourier functions. That's what we have chosen. And Fourier functions form an orthonormal basis. That was the point, that was the entire point of doing this, because we want the eigenvectors to be orthonormal as well. Earlier it was just orthogonal because any random symmetric matrix, they will have orthogonal, not necessarily orthonormal. But this, by doing this, we have normalized we have normalized the Laplacian in such a way that we, doing this eigen decomposition, whenever the basis vectors come out, they form an orthonormal basis. Okay, so so this is basically what this is. Laplacian times its eigenvector will be the column vectors and their particular eigenvalues, and the dot product of each and every uh, eigenvector with each other will be delta kk. This is delta function, such that when they are same it will be 1, otherwise it will be 0. So phi transpose phi will be an identity function. That is the important part. Eigenvectors, uh, matrix multiplication of phi transpose with phi will be an identity vector. And what capital phi transpose is? Capital phi transpose is just column vectors of capital phi is just columns of phi 1. This is phi 1, this is phi 2, and this is phi 3. Basically it's just all of the eigenvectors arranged in columns. That's what capital phi is. So, and lambda is a diagonal matrix with Laplacian eigenvalues. Sorry. Lambda is the capital lambda is the diagonal matrix with Laplacian eigenvalues, and on the diagonal are lambda 1 to lambda n, and from the normalized applications, these values are typically among the range from 0 to 2. Those are known as the spectrum of the graph. So this is the important part. We also wanted the lambdas, the eigenvalues, to lie between 0 to 2. And the first, it's possible that the first smallest eigenvalue is 0. And in fact, it will be 0 because addition of, this is just a side thing, you can forget it if you want, but the Laplacian, all of these rows add up to 0, so it has one vector in the null space, which is all ones basically. That vector will be in the null space, so the first eigenvalue will be, we can be 0, and the first ever non-zero eigenvalue and corresponding to that will be the Fiedler vector. This is all just additional advanced things which I've learned recently, and that I'm just imparting with you the knowledge. So never mind. Let's just forget about that. And the lambda will be the diagonal vectors of diagonal matrix with all the eigenvalues lying on the diagonal. So below is the example of checking the eigenvalue decomposition. The Laplacian matrix lambda is multiplied with the eigenvector phi k. This should be delta. The shape is result n cross 1, and the result is lambda phi k. That's just the way eigenvectors are defined, that uh, delta times phi k will be lambda times that phi k, and then lambda will be eigenvalue, and lambdas will be between 0 to 2. That's basically it. Now the Fourier transform becomes so easy to understand because of this particular notation. There are many benefits of doing it in such a way. So F Fourier transform of H will be just this capital phi transpose of H. Why? Why? Good question. Well then, why? Let's look about the inverse Fourier transform first. There will be some coefficient multiplied with our eigenvectors and adding all of those eigenvectors. What those coefficients are? Those coefficients are basically our own function dot product with each and every vector of the basis, right? We have a function and we want to change its basis to a new basis. What we do is how would we find the coefficients of that particular basis? We have a function we have a function h, and we want to find its coefficient in a new basis. All we do is just take dot products with each and every vector of that basis, and those are the coefficients that go along with each and every vector of that basis. So that's what we are doing here. That's what we are doing here. Phi k dot inner product with h. This will give us the Fourier transform. That is what the Fourier transform is, and that particular Fourier transform, when we multiply back with phi k and add them all together, will give us our h. So the Fourier transform is multiplying. If you're looking on the right hand side of the figure now, Fourier transform is multiplying each and every each and every eigenvector to the h dot product basically, and we can write all of these n dot products into one function, into one line. That will be capital phi transpose times the function h. That will be our Fourier transform h hat, and that is so easy. Just need to do one matrix multiplication and we are done. And similarly, going back to our h will be easy if not easier. We have our h hat, that will be our Fourier coefficients, and multiplying them with phi k and adding all of them together will give us h back, and this can be written easily as capital phi into h hat. So h will be equal to capital phi into h hat. This is just matrix multiplication. Here capital phi, please remember capital phi is eigenvectors arranged in columns. So inverse Fourier transform is capital phi into h hat, and h hat was phi transpose phi capital phi transpose into h, and with our earlier derived result that phi transpose will be an identity at all times, we can see that this results to h equals to h, and hence Fourier transform inverse and doing a Fourier transform on it will result in the same thing coming back together. So it's consistent basically, this is what I'm saying. So convolution now this is an important part. When we do convolution in time series as well, whenever we want to do convolution between two time signals, let's say g and h, to find the response, to find the impulse response of a system, what happens is instead of doing a convolution directly, instead of calculating that big integral of convolution directly, what we do is we do a Fourier transform and we multiply those Fourier transforms of those particular functions and we do an inverse, and that's what the convolution theorem states. The convolution theorem states that the Fourier transform of the convolution of two functions is the pointwise product of their Fourier transform. Okay, okay. So what this means? Fourier transform of convolution of two functions is the pointwise product of their Fourier transform. So let's focus on this. Let's calculate their Fourier transforms. Let's do their pointwise products, and the theorem states that that will be the Fourier transform of the convolution. So if we do an inverse Fourier transform of that particular thing, we will have obtained the convolution of those two particular functions. So instead of English, let's go into math now. We want to do convolution of a particular weight matrix with RH, with our graph. Now we were not able to do it directly because of those particular constraints, that there is no particular ordering in nodes, which is top right of what is top right of the viewer on YouTube, what is top right of the presenter behind YouTube, and there will definitely be cases when there are more than the neighbors of basically the neighbors of the convolution kernel does not meet the neighbor of our point. So basically those things did not allow us to do convolution directly. But what we can do is go into the spectral domain, do a pointwise product, and go through the inverse, and hence we would have obtained a convolution. That's what we are going to do here. First of all, we take a Fourier transform of our weights graph. Weights will also be like a graph, like this. This is basically our kernel. This will be a W in that image. So Fourier transform of this, Fourier transform of H, that is our own graph. Do a pointwise product and then do a Fourier inverse. So F Fourier transform of W will be phi transpose that W. Fourier transform of H will be phi transpose that H. Do a pointwise product and pre-multiply it by phi, and hence we would have obtained convolutions. So this pointwise product is, instead of writing it as a pointwise product, I want to write it as a matrix multiplication so that I can bring it inside, and so that I can do some clever manipulations on this. Instead of writing it as a pointwise multiplication, I just split it into a lambda, where lambda is just a diagonal matrix. So nothing is lost when I am doing this, or let's say I'm not doing any harm, because earlier it was just a pointwise product on two columns. Now it's a matrix multiplication where there is only one element per column and one element per row. So nothing is harmed when I'm doing this. So W hat is the Fourier transform in the of the graph, and we are going to multiply it with phi transpose H, that is the Fourier transform of our graph, and W is the Fourier transform of our kernel. So phi times W hat times this plus this whatever. Now I'll try to I'll bring this phi inside, and I'll bring this phi transpose here, and what happens is this is nothing but the weight matrix, the kernel matrix acting on phi lambda phi transpose, which is nothing but our Laplacian. So basically all this reduces to take a weight matrix and calculate on the Laplacian and multiply it with our function h, matrix multiplication that is, and we will have our convolution. This will be an n cross 1 vector, and we have our convolution ready. So that's it. We have arrived here, and inverse inverse graph Fourier transform is also easy. We go back from here, and we have basically learnt intra and inter things in this entire graph. So what about this then? What about, okay, we are covered till here. So what about FC, and what about this forecast backcast thing? So FC here is fully connected layer. Those are dense layers in a neural network. And what are they trying to do now? So we are also doing backcasting here to get a sense of how the model fits on previous values. The second GNN layer is forecasting errors based on backcasting errors. Similarly, okay. This is a bit. This is way too many words per slide. So let's try to see what's going on in this figure. Let's try to understand with a figure. They After our inverse graph Fourier transform, we are going up in this diagram, right? So what FC is just fully connected layers, and what forecast is that we are going to give forecast, that we are going to predict values in the future, basically. Okay, fair enough. But why do backcast? Well, backcast they are doing in order to see basically how the model fits to the previous values. Here, fits is not in the traditional sense of deep learning, where a function fits a loss function fits another function. That's not what fitting here is. Fitting here means this: if I have a time series with points this, and my graph, my forecasting model gives output. Can I change the color? My output is this, and this. So this backcast is in order to see how much error could have been produced when we would have been in the past. So this is a very would have been, could have been concept, but that's what it is. They're trying to backcast. Now what they're doing is, first of all, the forecast is going directly ahead, and the backcast thing is subtracted from our actual signal. So basically now we have these errors, which is going into the second StemGNN block, second StemGNN block, and from there we are forecasting errors. So basically their idea is just give raw forecasts and also give the user what can be possible errors in forecast and subtract those errors. So in order to refine our forecast one more level, we are also going to produce what possible errors could have been in a particular forecasting and subtract those errors from our original forecast in order to give a better refined forecast, so to speak. So that's what our output is. This ResNet kind of connections, skip connections, these are all just trying to give a refined, a better forecast. So first of all, direct forecast, then forecast our errors. His x minus x1 hat is nothing but what these errors could have been in the backcast. Forecast those errors and add them to this in order to, well, add in negative sense in order to give that, in order to reduce. So what they're trying to see is if if we are producing so much error in the backcast, it's reasonable to say that we can also produce so much error in the forecast. So calculate those forecast errors, or should I say errors forecast, and subtract it from the original so that we get, so to speak, an error-free forecast. And then we add those errors backcast to our original signal, original backcast, and give us a total backcast loss. So that's how the loss function is figured for this particular training. Now let's get a sense of what this text is saying. We are also doing backcasting here to get a sense of how the model fits on previous values. Again, fits is not the traditional machine learning fits, it's this time series fits. The second GNN layer is forecasting errors based on backcast errors from the first GNN layer and then subtracting these error forecasts from the forecast. Okay. Subtracting these error forecasts from the forecast from the first layer, thereby refining the initial forecast. I hope this makes sense now. So the second GNN layer is forecasting errors. It is forecasting what the errors were and then subtracting these error forecasts from the forecast of the first layer, thereby refining the initial forecast. Similarly, we also add these backcast errors to our first layer backcast to improve overall model backcast or fit. Okay, too many casts and too many backs, but that's what it is. Now, how the training is configured? Well, training is configured in such a way we have a forecasting loss, which is after all of this backcast forecast thing, we have a forecast loss such that y hat is our output, and we have a pure forecast loss, and then we have a backcast loss based on a rolling window strategy. So they have taken a rolling window of some time points and they are taking only those time points per series and moving it one at a time. Inference is done one step at a time by assuming model output as the true value, continuing with a rolling window. So the whatever the model outputs, that is the true value, let's assume, and then continue the entire thing again, and that's the way inference is done. Okay, so here are the results with StemGNN and with the others. So we can see that in the bold, we see StemGNN outperforming others, other forecasting methodologies, multivariate forecasting methodologies on almost every data set and almost every metric, except in will here deep state is performing better, but not by much. I'll say a percent, 1% of loss increase is not that significant given the between the first and second, the third one is 2% down. So this it's not so bad. Similarly here it's not so, it doesn't seem so bad. Given the number 3 is almost well, number 3 is also not too bad. So anyway, StemGNN is up there, so to speak. It's up there in almost each and every data set. And they also did an evaluation study, where evaluation study means what would happen if we were to not do this. So basically, if we were to not do a latent correlation, if we were to not construct a graph and directly assume all of these time series in a standard simple graph, the error increases. What if you were to not do spectral sequential cell, that one with the discrete Fourier transform and 1D convolution, well, the error is increasing. What about without DFT? What about without GFT? What about without residual? What about without backcasting losses? So as you can spend some time on this slide and you can see how removing each and every block in this particular neural network does not improve its performance. It's only decreasing its performance. So it seems, well, initially it seems that all of these seem to be important to the entire architecture. And yeah, that's pretty much it. That's pretty much it. And I hope I have given you an understanding of spectral temporal graph neural network for multivariate time series forecasting. Spectral temporal graph neural network for multivariate time series forecasting. That is pretty much it.